Hello world, it's Siraj, and we're going to try to predict earthquakes in this video using data science. Now, this is an ongoing challenge on the popular data science competition website Kaggle. It's called LANL Earthquake Prediction, and the idea is to use an existing data set of seismic activity to try to predict when an earthquake will happen. And there are people, this is an ongoing challenge, there are people who are, as we speak, submitting their best work to try to predict an earthquake using this provided data set. And in this video, we have three learning objectives. The first learning objective is to get some idea as to how to think like a data scientist. That's the first one. The second one is to understand the CAT boost algorithm, which stands for categorical gradient boosting. It's very popular. Don't worry if you don't understand that. We're going to go into that. And the third objective is to understand the support vector machine algorithm, specifically support vector regression, not classification, which it's usually used for. So those are our three main learning objectives. There's going to be a lot of math, there's going to be code, and we're going to do that all in this video in a 7-step process, as you can see here. We're going to go from zero, installing all of those dependencies, to exploring the data set, and then implementing the math and the code, etc. So it's super exciting, and if you haven't, subscribe. Okay, so let's get into this. So our first step is to try to understand the background of this problem. So predicting earthquakes has long been thought to be near impossible, but if we were able to predict earthquakes, then we could save countless lives and properties. These are very destructive forces of nature. So there are many ways of predicting the magnitude, which equates to how destructive an earthquake is. So we can see here our first equation for magnitude that I'm circling with my mouse pointer, log base 10 of A over A0. A0 is the base quake, the standard calibration earthquake for testing purposes, and A is the intensity of the actual earthquake. So when we divide those two values and take log base 10 of them, we get the magnitude. And there are different ways of writing this equation, as we can see here. We can denote it as I, we can set I equal to I base 0 times 10 to the m, etc. And so that doesn't necessarily have to do with this problem. It's just really interesting to note as background knowledge. So when we take that magnitude and we try to see what the places with the worst earthquakes are, we'll find that San Francisco is number 2, Chile is number 1, and this is a bad thing, right? So this is a picture of an earthquake, and we want to try to predict when this is going to happen. So the idea is that given seismic signals, we're asked to predict the time until the onset of earthquakes. Now, these earthquakes are actually laboratory earthquakes. So in the lab, 2 plates were put under pressure, and this resulted in shear stress. And we can see what this looks like by playing this little video right here, right at 3:24. He's demonstrating this process.
And then we push on the end of the sample and cause it to shear like that. And so that shearing would be motion on the fault surface.
So it's just like that, just like in the lab. And so we can see the training data is just a single sequence of signal, and it seems to come from one experiment. However, the testing data consists of several different sequences called segments that may correspond to different experiments. And we can see a preview of that right on the website if we go to data. And so here on this Kaggle page, we can see a sample of what it looks like. And all of these segmentations have a segment ID, and then there's a time to failure. Okay, so there are 2 features there, right? So 2 columns there. And so we want to try to figure out the relationship between those 2 columns. So before we begin, definitely check out these 2 helpful resources. So the first one is called Kaggle kernels, and what these are basically Jupyter notebooks, and it's a way for the community on Kaggle to share what they've done with this challenge, and they're super cool. Definitely check them out. They definitely gave me a lot of ideas as to how to approach this problem, and they will for you as well, how to think about this problem. It's a great initiative. And the second one is the website Papers with Code that the community is really digging, including me right now. And if you have an idea for a different type of model or whatever model you want to use, this is the website to search for, right? So let's say that I want to use, I don't know, genetic algorithms for supervised learning. Then I can just type in genetic supervised and see what shows up. Okay, so 2 papers showed up, and we can see the paper and the code, which is awesome. This website is awesome. I endorse this website. I approve this message. Okay, so So those are the two that definitely check those out, all right? So there we go with that. And now we are on to step one. Here we go. We're about to install and import our dependencies. So of course we need to install Kaggle because that's how we're going to actually retrieve this data set. And by the way, if you're watching this, I want you to open up colab.research.google.com and just do this with me because you can. This is all in the cloud. You don't have to worry about configurations or dependencies. It's all happening in the cloud, okay? So, I mean, locally, you don't have to worry about. So let's install that. And now we're going to install NumPy, but the latest version, to perform some math operations, specifically for statistical features, which we'll talk about. And lastly, we're going to install the CatBoost library, which will allow us to use CatBoost. Great, we installed that. So now that we've installed those dependencies, we can start importing all of the ones that we're going to use. So of course, we're going to import pandas because that's for data pre-processing. We're also going to import NumPy, which is going to be for matrix math. Now for machine learning, CatBoost, we're going to use just like we installed, specifically its regressor, because this is going to be a regression model, which I'll talk about. And pool, which I'll also talk about. And I guess for scaling, we'll want to use scikit-learn's pre-processing, what was it called? Standard scaler. Standard scaler. What else? For hyperparameter optimization, we'll want to use grid search. That means finding those ideal hyperparameters for our CatBoost algorithm, also for our support vector machine. Speaking of, scikit-learn has that. Scikit-learn has everything, seriously. It's got it all. It's got it all. And for kernel ridge, okay, so I gotta talk about that. We're not gonna talk about that right now, but we will at the end. But kernel methods are a way of improving support vector machine predictions and making sure that we can create a classifier line or regression line in a feature space that we can visualize, or in a lower dimensional feature space. So kernel ridge. And then of course, data visualization, we're going to import, for this specific use case, matplotlib. Great, okay, so those are our dependencies. That worked, awesome. So now we're on to step two, importing our data set from Kaggle, right? So we wanna collect that data set. So to do that, we're gonna use Google Colab's own file access feature, which is awesome, which lets us import files directly into Colab. Now, once we've done that, we can create an object called uploaded that will receive the result of whatever we upload. And then we can perform this command line operation that will move that Kaggle.json. I'll talk about what I'm doing in a second. .kaggle and chmod 600. Okay, so what we're going to do now is run this. And we're going to upload our Kaggle.json file. So what this is a way for Colab to know what your authentication details are. So the first thing you do is you go to My Account, and then you click on Create New API Token, and it will download that API token as a JSON file. So then we'll go back and we'll upload that Kaggle.json file. All right, so once we've uploaded our Kaggle.json file, we can access the Kaggle API directly using Kaggle competitions list. And it's gonna show all of the competitions that exist there. Now, that was just for, demo purposes. Now we can actually download the earthquake data. So great, now it's downloading that data directly from Kaggle into my Colab runtime environment. And once I have that, I'm gonna see where it is on my system. Looks like, okay, there we go, we got it. We gotta unzip this training file. So we'll use the unzip command to unzip it, train.csv.zip, and then we'll see what it looks like. And once it's done unzipping, we can see it right here, totally unzipped, and we can now go on to step 3, which is performing exploratory data analysis. So our first step is going to be to extract that training data into a pandas data frame so we can look at it, visualize it, and then eventually perform some statistical analysis on it. So for EDA, we've got our handy dandy pandas function here, specifically read CSV, one of the most used functions in data science. And we know the name of our file, as we can see it right above us. It's called train.csv. And how many data points do we want to import? This is a pretty big file, so let's just say 6 million, because why not? And then we're gonna say, well, let's name our data types. Our first data type is gonna be called acoustic data. And that data type is going to be an integer, 16-bit integer. And our next data type is going to be called time to failure. I mean, we can name these anything we want, but we're just going to call it that. And since this is a very floaty number, we're going to call it float 64. There's a lot of decimal places here. And once we have that, we can try and print out the first 10 entries. Let's say 10, and there we go. That's our data set right there, the first 10 entries, and these values are all going to change, and now our next step is to visualize this data. Now specifically, we want to visualize the first 1% of samples in this data. Now I've already written out this part in particular right here because data visualization is not super hard, right? We can do this in Tableau, drag and drop interfaces exist on Azure and all of these platforms, so I just wrote this out here. And when we plot this out, when we compile this, we'll see that right before the time to failure, right before this blue line, this time to failure, that is when the biggest acoustic quake happens. So we know that there is a point before the actual earthquake where there's a spike in acoustic activity, seismographic activity. Now, if we were to visualize not just that, but all of the data, not just the first 1%, we'll see that actually right before the earthquake, which is this blue line, this vertical blue line, right before this vertical blue line, the earthquake, every time there's a spike in acoustic activity. So there is our pattern right there. And EDA, exploratory data analysis, helped us visualize this pattern. So we know that the way it goes is spike in activity, earthquake. And this just keeps happening. Other questions we could ask is this interval constant? Do any other factors affect this, right? We're framing our question by using exploratory data analysis bit by bit. So we've done that part, and now let's move on to feature engineering. But before we do that, I also want to give out a shout out to Anton Loss. So his kernel was really interesting. What he did was he had the intuition to say that the data looks like sound waves. It's oscillating, as we can see in this visual analysis here. So he converted it into an audio file, he denoised it, then he animated the wave and compared it to a dubstep song, which is interesting. So his idea was that, perhaps just like a dubstep song, we can hear the buildup of an earthquake before the drop. So that's a really cool kernel that I would definitely check out. It's right here. It's called Audio Analysis with Animation. He's got a bunch of samples here. We can even play it to see what it sounds like. And then we can play it to see what it sounds like with the dubstep. Okay, so interesting. Anyway, data is amazing. So now on to step 4, feature engineering. So remember, we only had those 2 columns, but there are a lot of features we could have that could help increase the accuracy of our regression model, which we're going to build in a second. So which features do we want to add? Now, there are a lot of tried and true features, statistical features, that have improved models in the past. So what we're going to do is we're going to add about 9, maybe 10 statistical features to our data set. So it's going to be a lot more features. And hopefully the idea is that this is going to improve the capabilities of our model. It's going to have a better prediction value. So let's do all of that in a single function called generate features, given our data set. So that's what we call it, generate features. And we're going to say strain is going to start off as a list, and we're going to continually append that list with a series of features. And I'll explain what each of these features are. So of course, the mean is the average value of our data set. The standard deviation tells us how spread our data set is from the mean. The minimum value is just the minimum value in our data set. Kurtosis, I'm going to explain in a second. That might be a newer one for you if you haven't been in this space for a long, long time. What else? Skew, that's a fun one. What else? Maybe quantile values, a quantile value or two, and we'll split it just like that, quantile. And that's it. Let's just add those. And we will now return what this looks like. And there we go. So let me explain what each of these features are, and then we're going to talk about how we can add them to our data set. So of course, the mean is sigma notation here. We take all those values and divide by the number of them. The median is the middle number, right? If when we order them sequentially, what is the middle number? The standard deviation tells us how spread out our data is. So here's a visual representation of the standard deviation. So here it says 99.7% of the data for this example case are within 3 standard deviations of the mean. So if this data set looked much more spread, this distribution of data, then it could be up to 15 standard deviations or 20 or a bigger number. So it's how spread our distribution is. That's the standard deviation. And the way we find that is to take the mean and subtract each data point, square it, add them all up together, and then divide by the number of data points minus 1, take the square root of the whole thing. That's our standard deviation. Kurtosis then uses the standard deviation to compute itself. We use the STD to compute kurtosis. And so the way this works is we take the mean and we say, take each data point minus the mean over the number of data points, and do that for as many data points as there are, sigma notation, and divide by the standard deviation to the 4th power. Now the kurtosis tells us it's a measure of whether the data is heavy-tailed or light-tailed relative to a normal distribution. As you can see in this picture, positive kurtosis is higher, negative is lower, normal distribution. And the reason this is important is because it tells us how many outliers we can expect in our data. Data sets with higher kurtosis tend to have heavy tails or outliers, right? So, and the opposite is true as well. And then there comes skew. So skew tells us the asymmetry of our distribution of data. So this can be positive, negative, or undefined. And lastly, quantiles are basically ways of dividing the range of probability distributions in our data, and we can have several quantiles. It's just a way of segmenting that data out. And there's a lot of statistical features out there. We could have added more, and it would affect our prediction in different ways. There's no way to fully know that. I mean, there's model evaluation techniques. We'd have to try it out. That's part of the fun, right? So there's that. Now in this line, we're going to add all those features to this data set. Once we have added those features to our data set, we can visualize the completed data set with the new features that we added using the describe function. So there we go. We've got our new features. They have been added to our data set. Boom. All right. So now on to step 5, cat boost. So cat boost. Let's start with gradient boosting because cat boost is a type of gradient boosting. So gradient boosting is a technique that can be used for both regression and for classification problems. both types. And it produces a prediction model in the form of an ensemble, that means many, a collection of weak prediction models. Typically they use decision trees. Now, I want to note that gradient boosting is not specific to decision trees. We just tend to use decision trees because they're easy to implement and they tend to give good results. But this is a generalizable technique that can be applied to any type of model. Here we go for regression. The idea, and let's talk about it in the context of decision trees for explanation's sake. So with gradient boosting, we start off with a single tree and we are training it on some distribution of the data. And it's going to build a decision tree out of that data, right? To be able to make a prediction about that data. Once we have that decision tree, it's not going to be perfect. There are going to be data points, parts of the distribution that are off, and that's the hidden state. It could be better. So we take that hidden state and we use it to create yet another decision tree. And so the idea is that we're focusing on those data points that are not as encompassed in the regression line or the regression model of the decision tree. And we're going to focus on those data points and more in the next decision tree. And that's going to create a hidden state, a representation of the data. And we're going to do that again, right? So we iteratively do that. And so the equation then becomes h of x, where x is all of the data, is equal to the first hidden state of x plus the second hidden state of x, which are the hidden states of each of these trees. So in general, boosting works by iteratively learning weak classifiers and adding them to a final strong classifier. And after a weak learner is added, the data is reweighted so that wrongly classified examples gain weight and correctly classified samples lose weight. So in this way, the weak learners are trained to concentrate more on the misclassified examples, as we can see in this image right here. Right, so gradient boosting is a type of gradient descent algorithm, and we can see this pseudocode explains it very well, right? So we have some data sample distribution D. And so for m equals 1 to m, where m is the number of base models we want to use, that's up for us to decide. We can train our base model from the training sample distribution, compute the error, and then adjust the distribution of the next model to make the mistake of the model more evident. Then we output the constructed base model and use that as the input to the next iteration for m models, right? So however many models we decide that we want to use. And that's the basic idea behind gradient boosting. Iteratively improving a bunch of weakly learned models until we get a final strong model that is better than the sum of its parts. So now on to cat boost, which is a version of gradient boosting. There's actually several types of gradient boosting techniques. XGBoost is one, AdaBoost, there are a lot. So Yandex is the Russian Google, and they use gradient boosting a lot. And they use it to power a lot of their services. So the idea is that for cat boost stands for categorical gradient boosting. So what they do is they say, let's handle categorical features automatically. So without any explicit pre-processing to convert categories into numbers, CatBoost will convert categorical values into numbers using various statistics and combinations of the existing categorical features and combine both the categorical and numerical features. And so there are some advantages. There's usually tends to perform better than the other types of gradient boosting. As you can see here, it has the lowest log loss values of the gradient boosting algorithms that we see here. So it's really popular. It's getting more popular. And the ELI 5 of this, as you can see here, is we model the data with simple models, and then we find the errors. These errors signify data points that are difficult to fit by the simple model. And for later models, iteratively, we focus on those hard to fit data points to get them right. And in the end, we combine all the predictors together by giving some weights to each predictor. So let's go ahead and implement this. Now here comes our handy scikit-learn library. Thank you, scikit-learn, where we'll use this pooling keyword to collect the training data, both the input and the output data. And then we'll initialize our regression model using the regressor keyword. How many iterations? Let's say 10,000. Our loss function is going to be, as the Kaggle competition suggests, mean absolute error. And the type of boosting we're going to do, of which there are many types, is going to be ordered. And now we go back and we will fit the model to the training data and the testing data. And print out the best score. And now it's training. And then when we see our score, we'll see that our mean squared error is 1.86, which keeps us in maybe top 300 to top 500. It could be better, but my point is that this is our first model, our first attempt. So obviously it's not going to be the best, and we'll just iteratively improve, right? So that's the idea, right? So then we could submit this for more. So let's go on to step 6, which is implementing our support vector machine and the radial basis function kernel. So in simple regression, we're trying to minimize an error, right? So regression models try to find the relationship between variables, right? One or more variables. And in a support vector machine for regression, we're trying to fit the error within a certain threshold. That's the difference. So the idea is that the blue line can be considered what's called the hyperplane. The red lines are the boundary lines. So the blue line is the line of best fit, where the red lines are boundary lines that we're going to decide by some value they're off from the hyperplane. And we're only going to consider data points within this margin. So only those data points. There could be data points all over the place. And so simple regression will take into account all of those data points. But support vector regression will only take into account the data points inside of that margin, right? And those margins are defined by the support vectors, which are the data points that are closest to the line of best fit. So that's our objective with the support vector regression. And the boundary lines we draw are either plus e or minus e distance from the hyperplane, where e is some value that we define. So we can define the equation for our boundary line as such. It's going to be where y equals mx plus b is the line, so we'll just add e or subtract e from that equation, and that's going to give us our line of best fit. So notice how there are some data points outside of that, but we're not considering those. We're only considering and fitting our data to those data points inside of those boundary lines. And that's a support vector regression. So a lot of times we have what's called a non-linear decision boundary. That means that a straight line cannot fit the data, which means our support vector machine is not going to work well. And so on the left, as you can see here, so ideally we'd like to have the data points separated such that if we were to classify or to regress the data, we would be able to linearly separate it or linearly create the line of best fit. How do you make a line of best fit for that data over here? It's hard. It's impossible, actually, in that space. So what the solution to that is to use what's called the kernel trick. And the kernel trick, a very simple way of thinking about kernels, they are a similarity function. Given two objects, the kernel will output some similarity scores. And we can use those scores to reframe the problem such that a linear regression line or classification line can either separate or find the line of best fit for the data. And there are a lot of different types of kernels, right? So, input space to feature space. There are many different types of kernels out there for SVMs: linear, polynomial, Gaussian, sigmoid. But in this Gaussian or radial basis, as we can see here, but they're basically the dot product of two vectors. We can think of it that way. And so this is the equation for the support vector machine, right? Where we have a weight value that is learned through some optimization technique like gradient descent. And then we have the mx plus b, the line of best fit format as well. These are support vectors. So that's the basic idea behind a support vector regression. And that is not it's not used as much or understood as much as a support vector machine specifically for classification. So I thought I wanted to shine some light there on that. Right? It's usually used for classification, where a linear decision surface called a hyperplane is used to separate these classes. So what we're going to do is we're going to build this support vector machine using scikit-learn, and then we're going to pick the ideal hyperparameters using a hyperparameter optimization technique called grid search, which is going to pick a bunch of values. For each pair of values, it's going to evaluate the validation error function, then pick the pair that gives the minimum value of the validation error function. It's basically going to try out the pairs until it finds the best pair for our model. And so what we can see here is that I've scaled those values. I'm using my support vector regression, SVR, And these are my, the possible values that I've defined for my grid search hyperparameter optimization technique. So it's going to try out the pairs of gamma and C to try to find those ideal hyperparameters for our model so that it's best going to fit the data. And grid search CV does that. The kernel is going to be the radial basis function, as we saw before. And then we'll make a prediction, and then we'll output the best CV score, which is right here. Now, obviously, we could do better. There are different types of models we could use. We only use 2, but remember, our learning objectives here were learning how to think like a data scientist, at least a little bit, learning about the cat boost algorithm, and learning about the support vector machine algorithm, specifically support vector regression. And we did that. So future ideas, we could try recurrent networks. We could try genetic algorithms. We could try ordinary differential equations and think about this as a time series where there's just irregular data, which ODE nets are great for. So there's a lot we can do, and it's super exciting. I hope you found this video useful. I'm gonna have a bunch of helpful links in the video description. What's a data science model you want to learn more about? Let me know in the comments section, and please subscribe for more programming videos. For now, I've got to find a lasso, so thanks for watching.